Yes, of course. No, each team has a number of cores. A team is what controls a streaming multiprocessor. Oh, of course. So your GPU, one GPU, has multiple streaming multiprocessors, multiprocessor, if you want, multiple groups of cores. An SM, each GPU. Each GPU has multiple groups of cores. These groups of cores, we call them streaming multiprocessors. Okay? Now, when it maps to OpenMP, teams are what's going to be mapped to the streaming multiprocessor. Each team is going to be run in a streaming multiprocessor. By default, each team has one thread. So it means that when you're on a given streaming multiprocessor and you have 50 cores available, you just have one thread. So you will just be able to use, by default, one core in that streaming multiprocessor. If you want to use all the cores, you need to use many threads. So that's why you need parallel. Yeah, that's the tricky bit. When you switch to GPUs, it's this multi-level approach now, which effectively is the same on CPUs, but we rarely think about it on CPUs. But if you look at the node on bridges, the one you're currently having, I think it's 2 multiprocessors, each of which has, 64 cores or something. So effectively you have 2 groups of many cores. Yes, you can specify num teams, yes. Yes, num teams is just here to say how many teams you would like. Distribute is here to say that the iterations are to be split across the teams, regardless of their number. To make sure we're not getting too short on time at the end and we have enough time to complete everything, let's do this one step by step, slowly. It should be rather straightforward, this one. So let's see. So before parallelizing anything, first thing we want is going on the GPU. How do we get on the GPU? How do we offload to the GPU? Which one, sorry? Yes. Okay, let's put everything on there, so then we know we're on the GPU. Okay, so now we know we're on the GPU, fine. Now we want to use multiple teams. We're coming to this in a second. How do you create the teams? Yeah, I know. That's not the hardest question, but anyway. Now, how I need to phrase my question in a way that doesn't give you the answer. What could I have said? How could you share split? I'll try to use split next time. Distribute. Yes. let's go inside, and then we're going to take care of the other aspect. Okay, so now I have all my teams, and all my teams are splitting, distributing the iterations. Good. How do I parallelize the inner one, inner loop? Yeah. Indeed. Okay, so now everything seems to be parallelized. Multiple levels, that looks good. Now, let's try to think about, well, if I'm to execute this, it's not happy. See my reflex? Put the curly brackets. But it's exactly the same as parallel 4. Remember yesterday I said something that was really sad for me, was that after the parallel 4, you cannot put curly brackets, you must put the 4 right after. Well, the restrictions apply on this GPU as well. So when you write teams distribute, you must have the 4 right after, okay? No curly bracket. Again, makes me sad, but I'll recover one day, it's okay. It's happy now. And now what we have done when it comes to mapping is we are relying on the default behavior in everything. So if we're lucky, default behavior is more or less the one we were expecting. If we don't want to rely on luck, we may want to say exactly how we want the data to move. Yeah, something tells me it's not what we're looking for. So now let's see how you would move that data back and forth. You have a map, okay. How did you map it? So we have A and total here. So A, who says 2? Okay. Who says from? Nobody. So, and who says 2 from? Okay, so you said 2 from? Okay. Okay. After the target, I'm not using A. Yeah, go ahead, sir. Oh, yeah. Yes, in this case, we can even use alloc because we define the value actually inside the GPU. Okay? So you can have the alloc directly. Let's do alloc. We know how to do it after all now. Let's use alloc. Up. So, pragma OMP target enter data map, and we're going to have a 2D notation. Do we have the brackets or not here? Good. Oh yeah, it's not even a pointer here, so we're fine. Because it's statically allocated, we don't have to worry about anything. Yeah, I don't have the malloc this time. Typically, we use the enter data with dynamically allocated arrays, but we still have to free it, that's for sure. So to free it, pragma OMP target, yes? Oh yeah. Why? Because when it's statically allocated, at compile time, you have that data. With malloc, the reason you need to pass the length is because when you compile it, in our case, in the example, yes, it was hard-coded that it was going to be an array with 2 elements. But typically, when you use malloc, it's because you cannot see it coming, how many elements you're going to have. It might be the user going to say, oh, I want 500 elements, so you need to wait until you run the program. That's why with enter data, you need to say how many elements when it's dynamically allocated. And I delete A. Okay. For total, what happens with total? A map from? Okay, who says map from? Who says to? To from? Why did you choose to from and not to? Because look, the sneaky thing here. We must give the original value, which is 0 in this case. Why? Because we're going to add onto that value. So it means we need to make sure that the original value is set to 0 and not something else. Okay, but we still want to bring it back. So to from. Okay, let's see if we have the right value or if it's complaining about something. If I made a typo somewhere, seems to be happy. Now let's see if I have a big crash somewhere. If that works, we're then going to move to the last topic. I'm watching, so it's not doing anything. Oh, it hasn't finished yet. Okay. Let's see that. Oh, interesting. There's something going wrong somewhere. A second level here. Have a second level here. What happened? We never said how we pass the data in the inner loop. And by default, it was passed as with the first private copies, blah, blah, blah. So it means that here we also have a reduction happening there, right? You've seen that? Reduction. How do I describe this reduction here? Plus and then, yes, the total. What about A? Because we're passing A in there as well. Who says shared? Private? First private? Getting a bit confused? I like, because I still have students doing it, but they don't dare to say it like, yeah, that's fine. If you're not confused by this, you're really good. Because I myself am slowly checking my code now to make sure I'm able to explain what's going wrong. So if you don't even have a doubt, yeah, sure. Okay. So this, do I need a copy per thread? No, they can all work on that same array here. Fine. So shared A. Good. We cannot share that, otherwise all the threads are going to have an issue here. So our teams get their respawn, that is shared. Yeah, of course it's shared, it's fine. They have their own stuff. J is fine, it's in there. I is the copy, so first private here. Who says shared for I? Who says private? Who says first private? Yes. First private 8 with I. I don't know why the closing parentheses are just all yellow. If there's a Vim expert in the room, yes, go ahead. No highlighting. So which one is it? No HL and then search. Like that? Okay, because I knew there was no highlighting something, but I never remember the short versions. Thank you. Okay, final device map we allocate. The default variable is fine. That's allocate here. We set the values there. Total plus equals. Now we need to bring it back. Yes. Yes. No, we don't share it outside. We don't share it outside the loop. In this case, it's declared outside the loop to make you practice this allocation and everything. Oh, no, it's allocate from to from. At this level, you mean? Or at this level? One? 35, okay. Yeah, so here it becomes shared because we want all the threads to work on the same array to avoid copies, unnecessary copies here. Yeah. Oh, and now follow me here with this multi-level. That's probably the trickiest moment in the entire session, okay? Even what comes after is less tricky than this. So, right now, I have in each room, they have managed to do the reduction, okay? So I have the leader of each room that says, oh, the total for us is 14, the total for us is 79, and so on and so on. Now I need to propagate back all these totals to put a single total value, which is the one I print at the end. Okay? So effectively, I also need to use a reduction here. I think. And that's the moment where I am slowly... Okay, it's not complaining at this one, at this moment. Okay. So I think this reservation, this GPU reservation expires at the end of the session. I'm not sure. But after that, you can still submit all the same. You just cannot use a reservation anymore. But you will be able to submit to the GPU nodes like everybody else does, like the other users of bridges right now. You may have to wait a bit longer because you may now have to share these nodes with more users, but eventually you'll be able to submit all the same. It crashed. Ah, now that's a number I like. Okay, yes. Ah, yes. We also didn't put that on the outer loop, but it was still working. Okay, does it automatically propagate it? If I remove the reduction here, well, so I'll try to spend no more than 40 seconds on this because I have 2 more topics. Reduction, so we have the reduction at thread level, so each SM is going to have a reduction. No, because what I think is by default, scalars, total is a scalar, by default it's passed as a first, the weird kind of first private. So it means every team was working on a copy. So I'm not sure I understand how it propagated it back, unless OpenMP did some analysis and realized you were doing only reduction to the only thing that was inside this distribute, so it automatically propagated it back. I need to investigate this further. Just to make sure we cover all the topics, we're going to have fun with multi-GPUs now. It's about time to use more than one GPU as well. So, the same way CPU nodes contain definitely more than one CPU, GPU nodes now typically contain way more than one GPU. On bridges, not AWS, sorry, on bridges it's 8 GPUs per node, so you have 40,000 cores available. So using a GPU is good. If you can use all of them, it's way more fun. So you may say, yeah, but how do I even do this? The way it works is, by default, one of the devices, so one of the GPUs in this case, is selected, okay? You can check which one is selected. The GPUs are assigned identifiers like teams, like threads, so, okay, so 0, 1, 2, 3, and so on. So by calling OMP get default device, you'll get the ID of that default GPU that all your target go to. If you can get it, you can change it, okay? So if you want all your next targets to go to a different GPU, you just change the default device and you're good to go. The same way, you could check if you are on the initial device, you can also check which device is the initial device. That may seem weird. The initial device is the host, remember? The host, in accurate terminology, is nothing else but another device. It's not a target device, it's a host device, but it's still a device. So it also has an identifier. Typically, its identifier is -1 or minus something. Why? So that it doesn't clash with the GPUs, which can be then numbered nicely 0, 1, 2, 3, and so on. Okay? Try to guess the function to get your device ID. For threads, OMP get thread num. For teams, OMP get team num. For device, yes. I know it sounded like it was a trap, but no. I can also not be sneaky. That's possible. And how do I find the total number of devices? Exactly. So that returns number of target devices, okay? It doesn't return the host. So if you have 8 GPUs, it's not going to return 9, like, oh, 8 GPUs plus yourself. No, it will just return 8 GPUs. You may want to use multiple GPUs if you start to split your workload, okay? Let's say you have really massive arrays that you just can't process on a single GPU. The same way, if we use multiple nodes in the first place, is because single nodes are not able to have enough memory or computational power. It's the same thing, okay? Now, you can ask for a specific target to be run, to be offloaded to a specific device, okay? Just by using the device clause. So you say, oh, this target goes on device 0. Regardless of what the default is what applies if you don't pass device. If you clearly say device something, it will go there, okay? So now, exercise time, where you will have quite a few very simple questions in the exercise, and it's like, how do I know if I'm on the GPU? How do I know the default GPU? How can I change the default GPU? Okay, try to do something on your 2 GPU. So it's very simple. It's one line answer every time, typically, but it will get you all the scenarios and basically give you kind of a survival kit. You can just take this exercise with you, and that should fix all the situations you would have in future on GPUs. Let's show that. See, it's what, 8 or 9? Yeah, 8 printfs, and it's like, please tell me how to find the initial device number and everything. So it's just for you to have an example of each, so then you can refer to it forever. Your cheat sheet, as we say. Okay, who found the first one? You can still work on the other ones while we go step by step together for the first ones. Sorry? Initial device. What do I type? Yes. On this one, no. Just for this one, no. Who said it? I didn't. I can locate sound. Sorry. Yeah, but that's definitely a must-have for the next one. So you're again you're a bit too fast. You're definitely on point. Definitely on point. Because to get which device is the initial one, I don't need to be on the GPU because it's going to be the host typically. So as long as I run on the host, I'm happy here. And even on the GPU, I think the initial device would still return -1. However, how do I get the total number of devices? What, sorry? OMP what? Yes. Oh, sorry. Get. Okay, there's a double get here, but let's remove that. And now if I do this one right now, what's going to be the answer? Oh, sorry. Actually, I said something incorrect, by the way. We don't need a target here. We don't need the target. We just need to make sure we run this on the compute nodes, which do have GPUs. If we run this on the login nodes, it's going to show us 0, because on the login node, we don't have any GPUs. But the actual call itself doesn't have to be on the GPU, okay? It will detect them from the host. That's okay. So we have the initial device number, the total number of devices. Now, the identifier of the default device. Okay, how do I do that? OMP get initial device. Good. Now, how do I offload this printf to the target? Yeah. Sorry? Oh, thank you. The default device, yeah. Yep. Get initial device was going to return the identifier of the host. Execute, offload to, okay. So how do I offload this line to the GPU, to the default target device? Exactly, just the target. Oh, did you put something after the target? Nope, just target, exactly. Yes. Pragma OMP target. Curly brackets. Okay. So how can I now send it to a specific device? If I take my offload here, exactly. Okay, that's the first one. Here goes the second one. Okay, now how do I change the actual default device? OMP something, yes. Something, default device, yes. No, get is I get it, but I want to change it. Set, yes. So let's say we want to change it to the number 1. Okay. So I just pass my default device num. Okay. So now I still need to actually offload the printf to the other one. I don't even need to offload actually. Let's now try to retrieve that default device number. So we just changed it. So to check that we actually did change it for the value that we hope we just did change it to, how do I get it back? Exactly. Okay, and we just store the result of this in that. Okay, well, that's quite a few functions. It's nothing complicated, it's just that it's many functions in the same exercise, so that it shows you a bit of everything. I make, I submit, I run. Let's see where it takes up to now. So effectively, this is how you can send the first half of your array to the first GPU, second half to the second GPU, and something. And we're going to finish with another dimension to all of it. So the host device is device -1. Yes, that's in line, so that all your GPUs are numbered 0, 1, 2, 3, 4, 5, and so on. Okay? You have 2 target devices. Why? I thought there were 8 GPUs on a node. Because in the submission script, I asked for 2 GPUs. Okay? In your submission script, you asked for the number of GPUs you would like. I was not going to take all 8 GPUs for this exercise, but if I change these 2 to 4, it will say, oh, you have 4 devices. Okay? Which means you can write a code that can automatically adapt to the number of devices. No matter how many you get, if I send 2 or 32 or 3,000, your code will be able to use all of them every time anyway. Okay, that's where it becomes interesting. Default device is 0. That makes total sense. First GPU is the default. We offloaded something to it. We offloaded something to device 0, device 1. And when we changed it to 1 and we retrieved the value, we retrieved 1. Perfect. That's exactly what we're looking for. Yes? Which one? All good? Ready for the last topic? Still alive? Because that's just for fun. Who didn't know OpenMP before yesterday afternoon? Poor. Okay, you've had an introduction that is because in 6 hours like this. Okay. Well, if you survive this, you're good to go. Okay. Well, final topic now. You know that you probably already know a lot more of OpenMP on GPU than many people, right? Because OpenMP on GPU is fairly new. It's hard to find people who teach it. Teaching it or learning about it alone is quite tricky. When you have all these data movements. Yes? A bit louder, please. What do you mean replacing? As in the trend? Yes, absolutely. In CUDA, you write what we call kernels, GPU kernels, which are just, or shaders, which are just GPU programs, okay? And then you execute them, you launch them, as we say. OpenMP does the very same thing. I highly suspect OpenMP, especially on NVIDIA GPUs, to effectively, behind the scenes, write the CUDA programs and launch them. So yeah, they're doing the same thing here. Okay, what we've done so far, everything we've done, is remember the very start when I said target was synchronous, and I said, don't worry, I will come back on this at the very end. That's the very end. So by default, all the targets are synchronous, which means when I call target, I, the CPU, will wait and not do anything until the target finishes. If it takes 3 hours, I'll wait for 3 hours, which is not very good because it kind of blocks resources, okay? So you can use no wait. What no wait does is, I'm the CPU, I see your target, so I know there's going to be some code to execute on the GPU. So I'm like, okay, start to work on it, and while you do this, I'll move on with my life and I'll execute the rest of the code. Okay, now we're launching it asynchronously. So you don't wait for the end of it and you just keep going. Now you may say, oh, but how does it work then if I have multiple targets? Because that target may require the previous target to have updated something. So if I start multiple of them at the same time, it's all going to overlap and it's going to be problematic. If you have dependencies, you can express them with a depend clause. And it's very simple. You're going to express if you just read from a variable, or write to it, or do both. It's always the same thing. To, from, in, out, okay? So this is an example here. Oh, I fixed it, nice. No, I did fix it, perfect. So what happens here is we say, the first target is going to write into A. The second target will read from A and write to B. Depend in A, depend out B. Okay? And the third target is going to read from A, depend in A, and write to C. Depend out C. So far, so good? Okay. Now, the way it works is, I have a target that outputs to A, and then I have two targets that read from A and are going to write to two other variables, one on each side. Now it tells OpenMP that these two targets at the end can run at the same time. They have a shared dependence, okay, dependency, but after that, they can execute at the same time. So it means you can even send one on one device, one on another device, and have multiple GPUs working at the same time, okay? Or inside your GPU, you can have multiple SMs working at the same time. So you can now, you may not realize just yet the number of combinations you're now able to do. Now, this is what your own experience, when you're going to play with it, is going to teach you. But you can do now more or less every combination you can think of, regardless of how complicated the GPU is or how many GPUs you have. Okay? My examples are always very simple, just to illustrate a specific technique, but now you can do fancy things. Yes? Yes, because it's going to create a synchronization that you don't need. Because if you say, oh, I have a dependence on this, and actually you don't, it means that I will not execute you. Well, okay, that sounds weird. I will not execute. I'm not someone violent. I will not execute you for real, actually. But I will not execute your target construct until that is satisfied. Yes. Oh, then it's even better, because it means I will not even have to wait for the first target to finish before I execute the other two. So these expression of dependencies allow OpenMP to create what's called a dependency graph, so they can know how to schedule the different targets, when each target has to finish before another one begins. If you don't have dependencies, you're telling OpenMP, you can start to overlap everything, have fun, which is what we love to have. There's something I call construct synchronization, but that's a bit tricky, so let's go for explicit synchronization, good old synchronization. Because you may say, okay, I have asynchronous, but how can I actually know when it's finished for real? Because it's going in the background, okay, but now I would like to make sure it's finished because I need the value back. We have a construct, OMP task wait. People who know task-based parallelism in OpenMP, we just stole it from the CPU part, because eventually behind the scenes it's nothing else but tasks. Okay, So when I write OMP task wait is going to wait for all asynchronous targets to finish before you resume execution. Okay, so all your targets here that were asynchronous, as soon as you reach line 16, so after the task wait, you are guaranteed that all of them have completed. Make sense? Yes? Okay, that goes for the Fortran. So then we have approximately 5-ish minutes to do the final exercise before I give you the summary, and we conclude this whole OpenMP training. Anyone has finished? Okay, already, okay. Feel free to continue. I will go step by step to do the first ones, okay? In case you're stuck, you can see one, it will help you. Okay, before we think about mapping dependencies, first thing is we need to offload it to the GPU, okay? How do we do that? Okay, pragma OM, I will be able to write this word. Pragma OMP target. Okay, so far we're on the GPU. Before we move to asynchronous or anything, what's the mapping here? From, yes. Sorry. Map from A. Okay, let me put my curly brackets so that I can sleep nice tonight. Better. So, now I want that to be asynchronous. So, no way, yes. Since it's asynchronous now, dependencies. So what's the dependency I have here? Exactly, out A. Okay. Let's go with another one here. What about B? Is it really same as A, really? Yes. Okay, just save time. Okay, now something different. Yeah, I'm going to start from scratch, actually. Start from fresh, I should say. On line 39? Oh, the map, yeah. I thought I had changed that to B, and I forgot, thank you. Okay, perfect. So, before we think about asynchronous or anything, mapping. We're on the GPU. Step 2, mapping. A and B. Who says 2? A and B, both variables. Who says 2? Okay, who says from? 2 from? Yeah, you're on it. 2, exactly. We just need to read from them. So 2 is sufficient. What about C? Who says 2? I'm almost called it now. From. What we met 2? You're right, it's from. Okay, now my construct is correct, but I want that asynchronously as well. So I'm asynchronous, and what are the dependencies of that target? So dependencies, okay, so I have dependencies A, B, C, okay? A and B, what is the type of dependency? Who says in? Okay, I can afford not to ask out. Okay, in for A and B. Yes, because we need to wait for these 2 variables to have their values updated by the other 2 targets before. Yes. What about C? Exactly. Okay, and now I can more or less copy that. And the other target is more or less the same. It's just that the output this time is not going to C, but into D. So the mapping can be copied. We read from, we don't read from A and B this time, we read from A and C. I need it. Well, in this case, it's not going to count for much. Why? Because there's no target coming afterwards. But okay, so now the only thing I need to finish this is I need to Exactly. I need to make sure that all of them are finished before I proceed. It's 12:30, so I'm going to finish this and we should be good. No mistake, it's happy. Let's try to submit. Oh, reservation. Yeah, it's 12:30, so the reservation is gone. That was punctual. Oh, it's 12:30. Technically, I should still have it until 31, but okay. Okay, so now I'm submitting to the normal GPU nodes. We'll see. Oh, perfect. I got one right away. Why? Because I just said my job is going to take 5 or 10 seconds. So my job can be run very easily. When you have 15 people queuing and you just say, oh, I have just for 2 seconds. Oh yeah, sure, here you go. That's a sneaky way to get first. Okay. C and D, we have a problem there. What is it here? Depend in A and B, depend out C, map to A and B. Oh yes, that's a sneaky one. That's one of the sneaky ones. I get caught in this the first time every time. It's because A and B, the GPU is going to set the values, okay? But when I call this, the values I have on the host are still 0, okay? It's not 1, 2, 3 yet. It's getting 1, 2, 3 on the GPU, but maybe they have not completed yet, so my values have not been updated yet. So the A and B that I send right away are still 0, so I send 0, 0. So of course, the results are all 0. How can I prevent this? By making sure the A and B are on the GPU and never move. So I will just use a data environment. Which one? I'll let you do that for fun on your own time. It will take you 30 seconds. If you have any problem, you can help me. You can ask me today, definitely. But I will not keep you for much longer because it's the end already. Yes? Yeah, you can also use a task wait before to force the first two to finish, but I would like to keep everything fully asynchronous. Okay, so you've seen how to offload your work to GPUs, how to also control the mapping and the transfer, how to handle multiple GPUs and do it asynchronously, even if all this was rather packed. You will likely have questions, so make sure you ask me or anyone, actually. Like for the CPUs, believe me when I say there's a lot more to see, especially the reverse offloading, which is where you start on the GPU and you offload to the CPU. You just reverse the entire approach. It's really fun. And anyway, so just like yesterday, as always, there's a survey again and again and again. Same thing here. It's the idea for me to know what I do well so that I hopefully try to continue doing it well, what I do wrong so that I try to stop doing it. I had a look, of course, I had a look to all the feedback from yesterday, and it seems that the out of the 6 criteria, 5 of them are at 95% plus, so it sounds like it's going well. There's one which was at 80%, which was it was taught at the right pace. And this one, I never managed to get beyond 80 something, even if I'm like 95 plus and everything else. Like, why? Because the audience is so diverse. You have some of you who are discovering OpenMP. You have some of you who know some of OpenMP, and I know that there are some people in the room who know OpenMP really well. Now, teaching to an audience that is with so much diverse background, it's extremely tricky to keep it interesting to everybody, even if they would need 3 separate paces. Normally, what we can do in training is what we call consolidated training plans, where if you're a beginner, you will have also this afterwards. If you're an expert, you will have also these exercises afterwards. But the summer school, we need to keep it rather short so we can discover multiple things. So I have to stick to this approach. Anyway, I had the students who asked me if they could ask me on LinkedIn. I'm like, sure. I wear 3-piece suits, but I'm not biting or anything. So if you would like to add me on LinkedIn, have fun, really, no problem. But for the time being, I think it's more than time that we bring this to a conclusion. And thank you for your time. I hope you liked the OpenMP. Thank you.